Dear friends, we are discussing sorting algorithms. We have already discussed two algorithms for sorting, namely insertion sort and bubble sort. The basic idea behind insertion sort is that a sublist which is already sorted, for that you pick the next element and place this new element at its relatively correct position in the already sorted sublist, so that we get an enlarged sorted sublist. The process continues. In the case of bubble sort, the elements are compared in pairs of adjacent elements, and in this way the largest elements bubble like water bubble towards their relative positions. The maximum element, for example, occupies its final position, the last position, only after a number of comparisons of the adjacent pair of elements. That is, the maximum element is obtained after a number of comparisons relatively placed within the list. Next we discuss selection sort. The difference between selection sort and the earlier two sorting algorithms is that in this particular case, in each iteration we get the maximum element just by one iteration of comparisons of all the elements with one particular element, and therefore the maximum element of the list is obtained in one sequence of comparisons. Once the maximum element is obtained, a sublist by removing this element is considered, and again the maximum of this new sublist is obtained, and the process is repeated. This is why this is called selection algorithm in the sense, or selection sort in the sense that it selects its maximum in the first instance itself. So let us come to the discussion of this through an example. Please look at the slide. We are given a list of 6 elements namely 80, 32, 31, 110, 50 and 40. Our purpose is to sort this list in increasing order of numbers. What we will be doing, we will be creating a new location, say max, in which initially we store the first element of the list, namely 80, and then we go on comparing with the subsequent entries in the list, and whenever an entry happens to be more than the current maximum, then the new current maximum is created by copying that element. And in this way, ultimately when we are compared with all the elements, we get the maximum element in the max variable, and we side by side note down its position also. Once the maximum and its position are known, the maximum is copied in the last position, or rather it is exchanged with the last element. So let us go ahead with this one. The max, initially the variable max initially is copied with the first entry, that is 80. Then this max is, that is 80, is compared with the next entry, which is 32, because 80 is more than 32, no change to the variable max. Then we compare this current max, which is 80, with 31. Again 80 is more than 31, no change in the current value of max. Again we come to the next comparison of the next value, which is 110. Now max is 80. The value of the current entry is 110, which is more. Therefore now the value of max is made 110, and its position is also noted, that is 4 is also noted. Next we go to the next entry. Now the value of current max is 110. which is more than 50, therefore we need not change the current value of 110. And finally we compare the current value of max, that is 110, with the last entry, which is 40. Again the max equal to 110 is more than 40, no more change to the value of the current max. At this stage we have the value 110 in the variable max, and its position is also noted in another variable, namely max position, which is 4. Now the positions, the values in the positions 4 and 6 are exchanged, so that the new list which is obtained is 80, 32, 31, 40, 50 and 110. Now 110 occupies the final position, which is not going to change for it through further iterations. Friends, now the sublist consisting of all the elements except the maximum element, that is 110, is taken into consideration. The whole process is repeated now for the sublist consisting of 80, 32, 31, 40 and 50. So in this case again max contains the value of the first position, that is first element in the list, that is 80. Again it is compared with 32, again with 31, 40 and 50. All of these new values are less than 80, therefore max remains 80 throughout and its position is 1. Therefore now the last position, that is fifth position, which occupies 50, is occupied by 50, is exchanged with the value in the first position. That is, after this exchange the list becomes 50, 32, 31, 40 and 80. And we know that by this process the maximum of the sublist reaches its final position, and if we suffix to it 110, the actual maximum, then we will be getting at least the last two elements are in sorted order. So next we consider only the sublist which is obtained by removing the 80 also. So the sublist to be sorted now is 50, 32, 31 and 40. So friends, again the process is same. We store the value in the first position in the variable max, and the max position becomes 1. Then 50 is compared with the next value, which is 32, but 32 is less than 50, therefore our max remains unchanged. Again we compare this with the next value 31, then again 50 being more, that is the current value of max is more, therefore again the max does not change. And finally it is compared with 40, but 40 again is less than the current value of max, which is 50, therefore max remains 50 and 50 is occupying position 1. Therefore the last element and first element are exchanged. After this exchange, the new sublist which is to be taken is obtained by this iteration is 40, 32, 31 and 50, and as we know from earlier discussion, 50 is the maximum element in this sublist, therefore it is left out of consideration, and the next iteration is to be done only on the sublist 40, 32, 31. Again the first element is stored in max, the value here is 40 and max position is 1. Again 40 max is compared with 32 and then 31, both being less than this, therefore the max remains 40, and now the position of max is 1, max position is 1, these are exchanged with the last entry, that is 31 comes first and 40 goes in the end, and in this way we will be getting 31, 32, 40. Again max will be storing 31, and max equal to 31 is less than 32, new value of max becomes 32. But 32 and its position is 2, but the new max of the sublist 31, 32 is occupying its right position, and finally we are left with the list of single element, no comparison, and in this way the selection sort algorithm sorts the given initial list. Friends, this can be written in the form of an algorithm as we have done already. So this, at this stage, we may compare the two algorithms, selection sort and insertion sort. Selection sort moves the entries very efficiently, in the sense the max is reached after comparisons of all the elements just in one iteration. However, in insertion sort, we have already seen the max is obtained after a number of iterations. On the other hand, these algorithms, namely insertion sort, bubble sort and selection sort, have their flaws. We will discuss the relative merits and demerits of these algorithms after some time. In the meantime, we take another algorithm which is shell sort. The shell sort is, the shell sort is given in the name of a mathematician, D.L. Shell, who framed this new algorithm in 1959. The basic idea behind shell sort is that the given list should be partitioned into sublists by taking positions which are differing by a constant number, and these sublists are sorted by some other algorithm, and finally these are merged. The idea will become more clear when we consider an example of sorting a given list using shell sort. Please look at the slide. What we generally do, that the positions which are taken into consideration for sublists for sorting are, say, differing by ink. That is, first position, if ink is taken as 5, then first, 6th, 11th positions will constitute one sublist, second, 7th, 12th will constitute another sublist, third, 8th, 13th will constitute another sublist. Now these sublists may be either very small and can be easily sorted. If these are not small enough, then again the similar process may be adopted within the sublists by taking increments smaller. So let us take an example in order to illustrate this method. Please look at the slide. Let us think that the list to be sorted is the one which is given in the first row. That is, the list consists of 13, 3, 4, 12, 14, 10, 5, 1, 8, 2, 7, 9, 11, 6. So friends, what we do? First of all, we take some number, say, and the number must be taken as an odd number, because if we take the even numbers, the repetitions of the same list may be occurring. Therefore, here we will take our increment as 5. What does this mean? That is, we will be taking the elements which are having 4 elements in between. That is, their positions differ by 5. So, one of the sublists will be 13, 10 and 7. Another list will be 3, 5, 9. The third list will be 4 and so on. That is on the position 3rd, then 8th, then 13, and like that. So friends, by this process, we will be getting 5 sublists. If we have taken increment as 5, the first sublist will be having elements at first position, 6th position, 11th position. That namely 13, 10 and 7. Similarly, we will have another list of elements which are on position 2nd, position 7th, position 12th, and like that. Now each of these sublists is sorted by one of the algorithms which we have already discussed. So the sublist, the first sublist, which consists of 3 elements, 13, 10 and 7. We know by either of the earlier algorithms, this sublist when sorted becomes 7, 10 and 13. The next sublist consists of elements at 2nd position, at 7th position and at 12th position. Thus, this list consists of element 3, 5, 9, which are already sorted. Then we take the third sublist. Third sublist consists of elements at the position 3, at the position 8, at the position 13. The elements are in this sublist are 4, 1 and 11. Now 4, 1 and 11, the sublist when sorted becomes 1, 4, 11. Then next we consider the list which is having elements at 4th position, at 9th position and at 14th position. The elements in this respect are 6, 12, then 6 and 8, and these when sorted become 6, 8, 12. And finally we are not left with 3 elements but 2 elements, namely 14 and 2, and these are at position 5 and 10. When these are sorted we get 2 and 14. Now their positions in the after sorting, their earlier positions are maintained, that is now 7 will become the first element, 3 will become the second element, 1 will become the third element, 6 will become the fourth element, 2 will become the fifth element, and 10 will become the sixth, 5, 7th and so on and so forth. We get in this process a new list which may not be sorted. Now for this new list, we will take increment some number less than the earlier number taken. Earlier, in view of the size of the given list, we took increment as 5. Now for the new list which has been obtained through this process, we will be taking increment something number, and as I mentioned earlier, if we take some even number, it creates problems of repeated sublists. So next we take increment as 3. That is, now we will be making sublists which will be 3 in numbers. In the first sublist, the elements at 1st, 4th, 7th, etc. are occupying. In the second sublist, the second element, 5th element, 8th element will be there, and so on and so forth. So let us have a look. The new sublist which is obtained by first iteration is 7, 3, 1, 6, 2, etc., which is given in the first row. Now we will be taking increment as 3, that is, we will be taking sublists in which the elements are something like this. In the first sublist, the elements are 1st position, 4th position, 7th position, 10th position and 13th position. The second sublist will be containing elements at 2nd position, 5th position, 8th position and so on. And the third sublist will be consisting elements at 3rd position, 6th position, 9th position and so on. So the sublist when sorted, the first sublist when sorted becomes 5, 6, 7, 11, 14. The second sublist when sorted becomes 2, 3, 4, 11, 13. And the third sublist when sorted becomes 1, 8 and 10. Again, once the sortings are there, their relative positions will be 5 will be occupying the first position in the new list, 2 will be occupying the second position, 1 will be occupying the first position, 6 will be occupying the fourth position, 3 will be occupying the fifth position and so on and so forth. That is, the new list after this processing will become 5, 2, 1, 6, 3, 8, etc., etc. And finally, the increment now has to be taken only 1, because initially we took increment as 5, we don't take even numbers, therefore the next increment was taken 3, and now finally the next increment will be taken as 1. So now what we do, we in one sense the whole of the list is taken into consideration, and then some of the earlier sorting algorithm is applied, and we get finally this one. Friends, this algorithm has been found to be useful in some cases. So we will be discussing this in some later stage for comparative study of the various algorithms we have discussed. Next we consider, so far we have considered algorithms in which initially we start with the whole list for the purpose of comparisons, and only through comparisons we rearrange but work on the whole list. Now there are two methods. The basic idea behind them, or paradigm behind those, is divide and conquer. That is, instead of considering the whole list in one go, you divide this into two or more lists, sublists in the initial stages itself. Go on dividing the new sublist into sublists and so on and so forth. And when just two elements are obtained, then you compare and find the relative positions of the two elements. So this is the basic idea behind a strategy which is called divide and conquer. Under these two algorithms are there. One is called merge sort, and the other is called quick sort. And both of these follow the strategy of divide and conquer. That is, if you divide a given problem, you are more prone to solve it easily as compared to when you consider whole of the problem in one go. So that is the basic idea, friends. So please look at the slide. What we do, we divide the whole list into two parts. One of the lists is called the left hand L denoting the left part of the list, and H called the higher end of the list. And then what we do, again division or dividing the new lists L and H is done, and ultimately when just two elements are left, we combine them. Under this, as I mentioned, there are two algorithms. One is merge sort and the other is called quick sort. So merge sort, what is done in the merge sort is that we chop the list into two sublists almost of equal size and then sort them separately. Afterwards, we carefully merge the two lists. The method is explained through the example. Please look at the example. I am now discussing merge sort algorithm. We have the list of 7 elements, namely 4 followed by 6 followed by 7 followed by 5 followed by 2 followed by 1 followed by 3. What we do? In the initial stage itself, without making any comparison, we divide the given list into two sublists almost of equal size, because in the case when the list length is odd number, you cannot divide the given list into two equal size lists. However, if the number of elements in the given list is an even number, then we divide into two sublists of equal size, and generally the two sublists will contain the two different parts in which the elements occur in the same order. So we get two sublists. One sublist consists of the first 4 elements and the second sublist consists of the last 3 elements. So the sublists under consideration are 4, 6, 7, 5 is one sublist and 2, 1, 3 is another sublist. Now instead of again comparing and sorting, no, we don't do it at this stage. Rather, again each of these sublists is subdivided into two sublists. So the sublist 4, 6, 7, 5 is divided into two sublists, namely 4, 6 is one sublist of the sublist and 7, 5 is the another one. Similarly, the sublist 2, 1, 3 is divided into two parts. 2, 1 is one of the sublists and singleton 3 is the another sublist. Now at this stage, friends, each of the sublists has not more than 2 elements. Namely, the first sublist consists of 2 elements 4 and 6. The second sublist consists of the elements 7 and 5. Third sublist consists of the 2 elements 2 and 1. And the fourth sublist consists of the single element. At this stage, the comparison and appropriate positioning takes place. For example, in the first sublist 4 and 6 are two numbers which are relatively in correct positions, therefore nothing is done. However, in the second sublist 7 and 5 are not in correct positions, so the exchange takes place, that is 5 comes at the position of 7 and vice versa. So now two sublists are sorted. 4, 6 is the first sorted sublist, 5, 7 is the second sorted sublist. However, again the elements are not in proper sorted order. Then 2, 1 is the third sublist, which after sorting becomes 1 and 2. And finally the last sublist having one element is already sorted. So after this sequence of steps we get a new list in which the elements are something like this: 4, 6, 5, 7, 1, 2, 3. Now again at this stage, we will be again repeating the process, and after repeating the process we will be getting ultimately, whenever we reach a stage where just two elements are there in the sublist of sublist of sublist, then we make the comparative statement comparisons and make the pair in appropriate order. So this is the basic idea behind merge sort, and we can write this in the form of an algorithm. Now we discuss the next algorithm, which is quick sort. Friends, quick sort is also a divide and conquer algorithm. Here also the lists are chopped. However, before chopping, some more work is done. In the case of merge sort, you saw that just simple chopping is done. That is, if the number of elements is even and the number is n, then you take n by 2 first elements in one sublist and the remaining n by 2 elements in the second. If the number of elements is odd, then you will be taking in the first list as n minus 1 by 2 plus 1 and vice versa. And the remaining elements will be there. The second list will be containing one element less. Quick sort does some more work in the initial stages itself, before chopping. And then starts the process. The process can be better explained with the help of an example. Please, this is an example. Please look at the slide. We have a list of, again, 8 elements. The list is 5, 3, 1, 9, 8, 2, 4, 7. Generally in this quick sort, what we do, we take one of the elements, not necessarily in the first position, not necessarily in the final position or middle position, some element from arbitrary position, and is placed, is exchanged with the first position. And once this is done, then we compare elements from the right and the left with the first element, which is called pivot. I explain it how it is done. That is, 5 is taken as a pivot, and we will start comparing this pivot with the elements starting from the left and the right. That is, we will have two variables. One variable I starts comparing elements from the left to the right, and j compares the elements from right to left. And I continues moving to the right till we get an element which is larger than the pivot. Whereas from the right to left we continue moving till we get an element which is less than the pivot. For example, in this particular case, I is 2 and the value at the second position is 3. However, 3 is less than 5, therefore we will move I further to the right. Now I becomes 3 and the value at the position 3 is 1. Again 1 is less than 5, therefore I goes further. I becomes now 4 and the element at 4th position is 9. However, 9 happens to be more than 5. Therefore, we temporarily stop incrementing I. And similarly, we will start moving from the right. That is, j has value 8 in the beginning and the value at 8th position is 7. And 7 happens to be more. Therefore, we will go to the left. When we go to the left, j becomes j minus 1, that is, j occupies 7. And the value at 7th position is 4. However, 4 is less than the pivot value 5. So what we did, while moving from left to right, we found the first element in the list which is more than the pivot, namely 5. And while moving from right to left, we found the first element which is less than the pivot, that is 4 in this particular case. So in this process, we have found two elements in the list, namely 9 while moving from left to right, and 4 while moving from right to left. While moving from right to left, we are attempting to find out a number which is less than the pivot. While moving from left to right, we are attempting to find out a number which is greater than the pivot, that is 9. Now we have marked the two positions which are occupied by the number 9 and the number 4. Now we exchange this, so that lesser number comes to the left and the bigger number comes to the right. So friends, after looking at the bottom, you find 9 and 4 in their original positions. But now these will be exchanged, so that the fourth position will be occupied by 4 and the seventh position will be occupied by 9. So after this exchange, we will be getting a new list. Now the values of I and j are respectively incremented and decremented, and the rule of stopping is again the same, that whenever you are moving I from left to right, whenever a number larger than the pivot comes, we stop, and while moving from left to right, the value of j is decremented till we get a value which is less than the pivot value. So in this process you can see I becomes 5 and j becomes 6, and the two values at 5th and 6th position, namely 8 and 2, are exchanged, so that the two positions are after exchange, 5th and 6th positions values become 2 and 8. Now this process continues till j becomes less than I. So this gives, friends, one iteration. Then we go, repeat this process, and ultimately the list will be sorted. So that is the basic idea of the quick sort. The word quick sort is actually a bit misnomer. Actually it was suggested by one of the greatest computer scientists, Dijkstra. However, in many of the cases when the lists are not sorted, this may not be that quick as this there. But before we come to that discussion, we will discuss another algorithm which is called heap sort algorithm. The heap sort algorithm is dependent on a data structure which is called heap. So first of all, we look at the definition of heap, and then we will briefly have an idea what is heap sort. So heap can be defined as a binary tree with keys assigned to its nodes such that the following conditions are satisfied. The binary tree is essentially complete, that is, except some of the left nodes, right nodes, all nodes must be there, and the key at each node is greater than or equal to the key at its children. The idea of a heap can be better explained through graphically. This is a heap in the sense that first of all it is a binary tree. Binary tree means each node has at most 2 children. You can see that the node 10 having value 10 has 2 children. One of the children is occupied by 5 and the other child is occupied by 7. Again, the node with value 5 has 2 children, namely one occupied by 4 and the other occupied by 2. Again, 7 is occupied by, has only one child. So whenever a tree, any node has at most 2 children, is a binary tree. And the second condition for a data structure to be heap is that the value in a particular node must be greater than or equal to the value of its children. So the value in the topmost node is 10 and its 2 children are having values 5 and 7, so the condition is satisfied so far as the node with value 10 is concerned. Next, the node 5 node having value 5 has 2 children which are occupied by the values 4 and 2. Again the condition is satisfied, that is the value in a particular node is more than or equal to the value of its children. Now we come to the value 7. Now the node with value 7, and the node with value 7 has only one child which has value 1. Therefore you can see that the condition that each node must have value greater than equal to the values of its children is satisfied. So the data structure which is shown in diagrammatically represents the data structure heap. What are the non-examples of heap? We have two non-examples of heap here. One is on the left, in which again you can see the value, first of all the 10, 7, all these conditions are satisfied, but the last condition is not satisfied, that except for the rightmost nodes, every node must have exact 2 children. Now you can see that the node with value 5 has only one child, whereas the requirement is there that only the rightmost nodes may have some of its children missing, but all other nodes must have exact 2 children. So the left data structure or diagram doesn't represent a heap because the node 5 does not have 2 children. Had we removed the node with 1 as a child of 7 and attached it as a child of 5, then it would have become a heap. Another example in which the value may exceed, that is one of the conditions is satisfied which is given on the right hand, that is every node except the rightmost all must have 2 children is satisfied by the figure which is given on the right of this. However, here the second condition is violated, that the value in each node must be more than or equal to the values in its children nodes. And here you can see the node with value 5 is having a child whose value is 6, therefore this condition is violated in this particular case. So this is also not a heap. So this is basic idea of heap. Now you can explain, give this definition in another way. Heap is an array H1 to Hn in which every element in position I in the first half of the array is greater than equal to the elements in position 2i and 2i plus 1. This actually is translated to the equal which is given diagrammatically. Friends, what is heap sort? What heap sort does? That it picks one by one the elements from the left to the right, and first of all it creates a heap, and then it starts sorting process with the help of heap by sending the maximum element to the top, which infiltrates downwards and like that. So friends, this is roughly, we will discuss this algorithm sometimes later on. Now we have discussed a number of algorithms. As I mentioned earlier also, if one of these methods had been the best out of all algorithms, in the sense that is giving better results, that one particular algorithm gives better results for all type of sequences, then other algorithms should not have been studied at all. The reason why we have so many sorting algorithms is that none of the algorithms is better than the rest of the algorithms for all type of sequences of numbers or sorting sequences to be sorted. How do we know? What are the criteria by which we judge whether a particular algorithm is better or worse as compared to another algorithm for a particular sequence? What may be the criteria? We know in computer science the time of computation, the memory requirement, and the difficulty of writing the algorithm by a programmer are three major considerations for finding whether a particular algorithm is better or worse than another algorithm. So in view of these criteria, we will discuss which of the algorithms, the sorting algorithms which we have discussed, perform better or worse. So again I repeat, in order to compare various algorithms, we will take into consideration three parameters. The first parameter is the time for the same sequence. Which algorithms takes more time as compared to the others. Second criteria is how much memory requirement is there. If an algorithm takes much more memory as compared to the other algorithm, then that will not be taken as a good algorithm. And thirdly, the complexity or the difficulty of writing the algorithm and understanding the algorithm by the programmer. So in view of these three types of, we will be discussing the comparatives. So please look at the slides. If we think that the length of the number of elements in the list is n, then the number of times the keys are to be compared by various algorithms and assignments. Friends, in this respect I may tell that our computational efforts are having two components. One is the, one is that the comparison of keys. You have seen in all those algorithms that we are comparing two numbers. And once a satisfactory situation is reached by comparison, then we exchange. So our time for sorting may be divided into two parts. One is comparison of keys and the other is assignments. Now we come to the slide. The various algorithms take this much time in terms of the length of the sequence. If the length of the sequence to be sorted is n, that is, if there are n elements in the given sequence, then the selection sort makes half n square comparisons, roughly. Order n shows roughly, approximately. And the number of assignments is, that is, the values are changed in the variables, is 3 times of the length. Insertion sort takes 1/4 of n square. That you can see that the number of comparisons is almost half in the case of insertion algorithm as compared to selection algorithm. However, in the case of insertion algorithm, the assignments are of order n square. I will discuss what is meant by order n square. But those are very, for example, if the number of elements is 10, then n square becomes 100. You can see that in this case insertion sort for large n's may be making more assignments as compared to selection sort. In the case of shell sort, the number of comparisons is n raised to power 1.2 to 1.6. You can see that the complexity of shell is a very complicated algorithm in which the computation of comparison of keys and assignments is very difficult. It is just done on the basis of experiments empirically, and you can find in some cases it is quite less because the power is less. So friends, with this we come to end of our second lecture on this sorting algorithms. We will continue our discussion in the third lecture today. Thank you.